Now, this correlation operation means what? You studied in 101 linear time invariant systems. We'll come back to it later, but just remember what we said in 101. The output of a linear time invariant system which choose an impulse response h of t is equal to correlation, a convolution between the input and the impulse response. So, any correlation operation basically means you have a black box with h of t and input is x of t, the output will be correlation operation, right. So, here I am doing a correlation operation. So, what I need to do is put this signal to a box whose impulse response is given by this square. The output of that will be that, and you multiply the output by this function, you will get the Fourier transform. Are you with me or not? So, what I am doing is, I am taking S of n, multiplying it by e to the power of minus j pi n square by n, passing it through some black box whose impulse response is e to the power of a pi by n square. How comes that summation? Now you multiply this by e to the power of minus j pi m square by n. This is your x of n. Pictorially. Is the point clear or not? Good. It should be m square. No, but when you plug in n minus k, it becomes automatically n minus k. When you put convolution, correlation, you put n minus k, right? So, in that you put automatically m minus k. When you do convolution, this has to be substituted by m minus n. So, what is the beauty of this? Beauty of this is, I put on samples like this, I get samples like this out. So, the real term, in some sense, a real time Fourier transformer. I put the function and I get the Fourier transform of the function. I don't have to wait for the computation to take place. As the signal is going out, going in, I get the signal out, which is the Fourier transform. This m represents the sample values, so I get samples, and the samples automatically will do Fourier transform. In some sense, they call a real time Fourier transform, quote unquote real time Fourier transformer. And there is a name for it. This is called the chirp G transform Fourier transformer. This originally was invented by Darlington in Bell Labs. for continuous signals, and then it is now translated into discrete signals by this. And in continuous signals, what this really means is a network with a phase characteristic which is omega square. Remember LTI systems, what is the transfer function? H omega into e to the power of j theta omega, and normally we would like theta omega to be directly related to omega, omega tau, so that there is no distortion. So, normally we would like it to be omega t, but here what we want it to be equal to omega square tau. So, this is called a dispersive delay line instead of a normal delay line, and fortunately for us there is a hardware dispersive delay line available called the SAW devices, surface acoustic wave devices. So, they use the surface acoustic wave devices to do this real world Fourier transform, real time Fourier transform. Are you with me? So, it is the greatest achievement in terms of radar. People use this structure quite extensively, because at those frequencies SAW devices are available. So, you can do Fourier transform on a real world, real time, and it does not require anything to do with the number being equal to 2 to the power of n. As it comes, whatever is the number, that how to comes the Fourier transform of that. There is no requirement. It is a beautiful system. Now chips are available which will do the chip G transform, which internally has hardware, binary hardware, which will give you that kind of impulse response. So, there is another method of finding Fourier transforms. Very simple idea that Mn can be expanded in terms of this, as simple as that. And it gives you some new insight into how to get real term. You just sit down and think what you are doing by Fourier transform. For every sample of the Fourier transform, you will have to have the signal available of n number of values, do some operation on that with the corresponding value of m, and then get a x of m for a given value of m. Repeat the same thing for every value of n, right? N square value times 2, but the signal must be available to you for a duration equal to the computational time. It reduces when you go to fast Fourier transform, you do not require that signal to be available all the time, but theoretically when the actual full Fourier transform is done, the signal must be stored somewhere, and you take the signal out repetitively n number of times and do that operation to get for output for every value of m. Whereas here there is nothing, it just goes in and out comes. So, you do not need any storage. It may be, it is quite obvious, there must be some storage somewhere in the impulse response of the system, obviously. Because by use of Fourier transform, I do not have a Fourier transform value until all the samples are available. X1 must be available for all values of n. And to say that I do not require all sample to get the Fourier transform is a wrong statement. But as long as I am putting it here in a sequence, doing something here, and some storage, some operation, something, and then giving out to you some output here. So, real world one will have some built-in storage somewhere in the delay line, dispersive delay line, because it has to be there, because till all samples come, I can't do Fourier transform, because it depends upon all values of n here. So, they must be coming into this thing, stored somewhere somehow, and then used in some manner to get output. So, in that sense, it is not a real term strictly speaking, but As you put in, you get the output here. Okay. So, this is the chip G transform. I give credit to Darlington, although the DFT people give it to somebody else, but originally it was done by Darlington. Okay. And there is another variant of this. I have 5 minutes more, which is again a brilliant way of doing it by Capon. It is a less commonly known system. J. Capon, he called this coherent memory filter. And he has used it for some sonar signal processing in some submarine requirements. So, he conceived of this coherent memory filter, which in literature you will not find it that easily. This also came up around 1960. Darlington also came around 1960. So, what he did was, you put x of n to a delay line or a delay register, each of delay equal to some tau, n stages of delay. You understand what I mean by delay? You put x of t, a delay of equal to that number of n times some t. Here you put a summer. I don't know, it's a brilliant thing how he got into his head, I don't know. So, he put this signal here, sample, it goes like this. Initially they are all 0, reset. So, the sample goes in at some instant of time. So, this is filled with x0, and the rest of them will continue to be 0. Let us take four stages. Then at next time interval, this becomes x1 and this becomes equal to, what happens? This time duration tau is not same as this time durations. This next sample comes at some n times tau. So, until n interval, this goes on shifting from here to here. So, x0 becomes here. So, this becomes here, this becomes here. So, after n shift, this will be x0, next one will be equal to, but then this one will be, and this continues to be the other one. So, it goes on doing this operation. Are you clear with? This is a register, it is not a just simple shift line, delay line. If x0 is put in, next interval of time, this also becomes x0, this and next interval, this becomes 0, x0, all of them will become x0, until the next one comes, which feeds this to x1. Are you with me? No. Very good. Let us take 3 taps. Initially 0, 0, 0. When the first x0 is inputted, this becomes x0 and this becomes 0 and this becomes 0. What comes out here is 0. Next instant it becomes, this is the starting point, this is 1, 2, 3, and then the next one will become x1, x0, x0, 0, the last 0. The next one will be x0, 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 but by that time this will have become x1. So what comes out is equal to x1, x0. And next one, this x1 will become, x1 remains here, x1 remain here, and this x1 will come here with x0 out. So this sequence goes, remember what you observe what you are doing. That means these two samples come as two samples. Two x1s will come out two samples here, x1, x1. So the output of this will be the same sample repeated n number of. And it goes on like this for n number of samples of x. Then see what happens here. It is not just only this, now we have feedback here. So this sample here, whatever is at this here, will be multiplied by something here. And that comes in here along with what comes in here. And that is now modified by this, the looping. So if you write down the equation, I will do it in the next class. If you write down the equation for this, it comes out to be beautifully the Fourier transform will come out at the output here. Here it will be just y of m, x of m. I don't know how we conceived of it, but so this system is what is called as the coherent memory filter.